Hello and welcome to the very last lesson of Unit 4 on exponential functions. Today we are looking at application of exponential functions. And so far you've worked with the functions, exponent rules, and graphing, as well as transformations of the graph. But now we're going to see where exponential functions actually appear in real life. So today you will be introduced to a variety of problems, especially including population problems. And the actual main application you're going to see in the next unit when it comes to financial literacy, where we will be using a lot of the stuff that we learned today, but in the context of financial literacy. So starting with our general equation here, and I have included this for you just to see, but after we go through the problems, especially the first problem where I walk you through step by step, it should make a lot more sense. But generally with problems involving exponential functions, you have an initial amount. So consider a population, you have the initial population at time t is equal to 0. And that population or amount is growing at a specific rate. So that rate is R. So for example, if a population is doubling over a period of time, or if it's decreasing by 5%, those are all the rates of change, and it will be per the time period. And units really matter here if you're using the time periods of years. You have to always work with years. If you're working with hours, you have to work with hours. And so t here will be our time period that has passed since t is equal to 0. And so, of course, this whole expression is a function of t, and we have our output, which is n of t, and it is the resulting amount after time t. So, for example, with the population, the initial population times the rate of change to the power of the time that has passed will give you the resulting population. And so, of course, when r is greater than 0, then we have this bracket is greater than 1. So that means we have an exponential growth. So our population, for example, is growing. Whereas when r is less than 0, we would have 1 minus r. So our value inside the bracket is actually less than 1. So then we have an exponential decay. And the value of R is written as a decimal. So whenever you have percentage, you do have to convert it to a decimal. So 5% will be 0.005, or negative 12% will be negative 0.12. And remember, this is just division. 5% is 5 over 100. So it's just dividing by 100, which means moving the decimal points over 2 times. So let's look at our first example here. We are told that there are 5,000 yeast cells in a culture. The number of cells grow with a rate of 25% per day, and the function that models the number of yeast cells, n, after d days is given by n of d equals the initial population, n0, and then 1 plus r, where r is that rate of change, to the power of d, and remember d is here days. And this I just mentioned, and 0 is the initial population, and R is the growth rate. And we're actually given some of these values. And we're asked how many cells will there be after 1 week. So with the given values, we of course have the initial population, and 0 is 5,000 cells. The initial number of days, so D0 is also just 0, so 0 days have passed. The growth rate, which is 25%, as a decimal is 0.25, and the number of days that we are looking at is d equals to 7, and of course we have the formula for that models the population. So before I calculate it, I did want to go through step by step for some of the days so you see what this really means. So consider that on the first day, when d is equal to 0, the population is 5,000. That means the next day, the population has grown by 25%, which means that 25% of 5,000 has been added to 5,000. So n of 1, so after 1 day, we have the original 5,000 population, but now we also have 25% of that population added. And really, if I factor out 5,000 from here, then this term gives me 1, and this term gives me 0.25. And this is 5,000 times 1.25, and so that means after 1 day, we have 6,250 cells. And already this is this formula here with D equal to 1. So we have 1 plus R, which was 1 plus 0.25, and to the power of 1. Now, using this value, the next day, so now D is equal to 2, and this is with respect to the first day when D was 0. So now the population has grown by another 25%, which means that now the population, N2, is given by 6,250 times 1.25. In other words, this is that 5,000 times 1.25 and now times another 1.25 because again, remember we want the 6,250 cells, but we're also adding another 25% of this value to it. And so this again is just a substitution here. Now I have 1.25 to the power of 2. And I hope you can see that this is again that formula now for n of 2. So we have 5,000 and then 1 plus 0.25, which was our rate of change to the power of 2. And so after day 2, we have 7,812.5. And of course, when we are working with cells, and I didn't include it here because that's not where we're stopping, but you do want to consider whole numbers. So if you were asked how many cells are there after 2 days, you would round to the nearest whole number, but you actually round down because you don't fully have 7,813, but you for sure have 7,812 cells. So based on what we just saw here, now we want to calculate after 7 days. So now I will just use my formula. So n of 7 is going to be 5,000 times 1 plus 0.25 to the power of 7. And so if I calculate this, this is 23,841.86. But again, because we are rounding down, then after 7 days, there will be 23,841 yeast cells. And that would be it for this question. The next part, we're asked how many cells will there be after 2 weeks. And so very similar to above, this part is just pretty much the same, except for D is now 14 because it's 2 weeks. So then N of 14, this should be, 2 weeks here. 2 weeks. So then we still have 5,000 times 1 plus 0.25, the rate of change, but now to the power of 14. And so you get this value. And if we round down, after 2 weeks, there will be 113,686 yeast cells. Now, just some questions for you to think about. First, if the growth rate increased to 30% per day, how would the population after 1 week compare? And you're asked to explain without calculating. So I don't expect an actual answer from you, but do you expect the population to have grown, or is it going to be more than when it's 25% or less than 25%? And you can even try it if you're not sure. And I hope you can see either through calculation or just using mathematical logic that if I have 5,000 times 1.3 in this case, because it's 30% to the power of 7, then of course this is going to be greater than 5,000 times 1.25 to the power of 7. So of course, as mentioned, when r is greater than 0, it is a growth. So of course, when you are comparing two rates of change, when R1 is greater than R2, then we also expect that the resulting population using R1 is going to be more than R2. And then I want you to think whether this model would remain accurate forever. And specifically in the context of like real life that we're talking about, can we use this formula indefinitely? Why or why not? So again, no, not really. It would not remain accurate forever. In real life, of course, there's many factors, especially when it comes to something like the population of yeast cells. There's many factors in the environment, including temperature, anything that the lab technician or whoever's dealing with the population, things that they can do to affect that population. So this can be an estimate and it can model our population for a period of time, but perhaps maybe in real context, it would not be accurate forever. So now with our next example, we have the population of a town was 2.5 million in 1960. The population has grown at a rate of approximately 1.3% each year since, and we're asked to create an algebraic model that represents the population of the town in the future. And specifically, we're asked what will the population of the town be in 2030? So again, we start with our given values. So the initial population, N0, is 2.5 million, or you can write it as 2,500,000. And the initial year, which was 1960, and here we have, and again, you can use D or T in this case. I just went with D here, but D0 at the year 1960 is 0. And so this is actually our start date that we're considering. So any time that we're considering after that is with respect to 1960. Now, the growth rate we're also given by 1.3%, so converting that into a decimal is 0.013. And so now the number of years in 2030, and so now again, with respect to 1960, this is 70 years that has passed. So then D is equal to 70. And so, of course, we're using the same formula. N of D is going to be equal to the initial population times 1 plus the rate of change to the power of D. And so considering in the first year, 1960, I did want to walk you through this example as well because it might be a little bit different when we're thinking of years and population. So after 1 year, the population has grown by 1.3%, which means that the population is now, and keep in mind here, I did write 2.5. I am in the back of my head, I do know this is 2.5 million, but I rather work with smaller numbers than to write 2 million out this way. So feel free to use 2.5 as well, but please don't forget that it is million. So when you are writing your final answer, it does have to acknowledge the million there. So of course we still have the 2.5 million, but now we also have 1.3% of that 2.5 million added. And again, factoring out 2.5, this gives me 1.013. And this was that formula there when D is equal to 1. And so then we have 2.5325 million or 2,532,500 people. And in this case, because it was millions and the decimals that I got actually fit with my million value, then you don't round down because clearly we can see that this is a whole number for the number of people. So we leave it as such. So then the next year, in 1962, D is equal to 2 now, the population has grown by another 1.3%, which means that now we have this population here, and now 1.3% of this population has been added as well. And so again, I'm substituting this part just from here. And so then I have 2.5 million times 1.013 squared because it's 2 times. And here we have this value here. And again, because we are working with millions, I will move my move my decimal over. And here, when I move the decimal point over, I actually do see that 5 at the end there will result in a 0.5. And again, we don't have 0.5 people. So here I would round down and we have 2,565,422 people after 2 years. So in 2030, after 70 years, then we use the formula, and of 70 is going to be 2.5 times 1 plus 0.013 or 1.3% to the power of 70. And of course, we get this value here. And so moving my decimal point over 6 times, I would end up, okay, like that. So that 312 at the end is going to give me the decimal for the number of people. So that's the part we omit. And so in 2030, the population will be 6,174,491 million people in the town. And of course, these are super helpful for people who work for cities if they want to be working on city planning. It's good for them to have a model that represents how much the population is growing by in order to estimate by after a certain number of years how much population they expect in a specific town or city in order to accommodate for that number of people. But of course, it isn't this simple. They do have other factors. Especially when it comes to population, they have to consider immigration, emigration, births and death rates, and um, other factors that affect the population to make this estimate. But for our case, this is a simple model that gives us that population. Now, this next part is a little bit different. It's asking us to do the opposite of what we've been doing. Now they've given us the number of people, and they ask in what year was the population 4.2 million people. So again, beginning with our initial values, we have 2.5 million people as our initial population. The initial year is 1960. The growth rate was 1.3%. And the resulting population in year D, and we don't know what year D is 4.2 million. And so the reason I use X here is because you don't want to use that same D. D is just a placeholder. So to say it was a specific year, I did use X here to represent it. So I want to know then for what D value specifically, I'm going to end up with 4.2 million. And of course, my model formula as well. So pretty much we want to find N of D that is going to give us 4 million, 4.2 million. And again, we are using 4.2 million and remembering that it is a million value when we are interpreting our results at the end. So using the formula, 2.5 times 1 plus 0.013 to the power of D is going to give us 4.2. And first, I'm going to simplify the bracket to give 1.013 and dividing by 2.5 because the variable D is not or is not dependent on 2.5. So then I end up with 4.2 divided by 2.5 or 1.68. And really, I'm trying to solve for what exponent D is 1.013 going to give me 1.68. And actually in math, there is the opposite operation for exponent, and it is logarithms. But logarithms are not a requirement for this course. I do show them to you briefly in our next unit, but for the sake of these questions, and you won't have a lot of them, just a few examples for you to see, you can just try trial and error to get the best estimate. So you would just be trying different values of D to see which one gives you the closest. So that's exactly what I've done here for you. D is equal to 10 gave me 1.013 to the power of 10, which was still not enough, and it's actually pretty far off from 1.68, so I have to try a higher value. And also, since I have done part A, I for sure know that it's less than 70 because 70 was 6 point, about 6.2 million, and I'm looking for 4.2 million. So it for sure should be closer to 70, but again, assuming we hadn't done part A, you can always just try different values that you think would work. So 10 didn't work, we try a higher value, and of course, because it was pretty far off, I jumped to 30 instead of trying 20, and then I got 1.4732, which is closer to 1.68. So keep in mind, this is what we're trying to get close to this time, but it's still not quite enough. So then I try a slightly higher value. Again, I'm going by tens, so now I try 40, and I actually see that I get a really close estimate. And again, because you're not solving for an exact value, then it would be sufficient to leave it as the closest value that you can estimate. So here we would say 40 works. So after 40 years, and because it was 1960, then 40 years from that would be 2000. And here I did do a check as well. So N of 40, if I substituted 40 in my exponent, I did get approximately 4.2 million people. So then in the year 2000, the population will be 4.2 million people. And for those of you who are curious about logarithms, I will just show you how it would look like. So you would be solving for this, which tells me that When I have a base of 1.013, what exponent do I need to get 1.68? And so if you solve for this, you get 40.166. And that's actually really close to 40 as we expected. And again, because with these problems, we want to have an estimate, then even if you had got this, you would have just wrote 40 anyways. You can say after 40 years, the population will be 4.2 million because of course, after a few months, it will be like a bit more as well. So approximately 40 years would have worked there. Now, our next example here, a hospital uses cobalt-60 in its radiotherapy treatment for cancer patients. Cobalt-60 has a half-life of 5.2 years. That is, every 5.2 years, 50% of the original sample of cobalt-60 has decayed. The hospital has 80 grams of cobalt-60 and requires at least 64 milligrams for the therapy machine to provide an effective amount of radiation. And we're asked how much of the original sample will be there after 1 year. So lots of values are given to us here. And of course, looking at this problem, you see a lot of different numbers. So that's why it's also important to interpret our values at the start and write what is given to us and also determine what we are trying to solve for in order to determine which of these values are actually helpful for us. So we know for sure the initial amount is 80 grams and the rate of change is 0.5. And actually it's negative 0.5 because it is half-life. So it means our population is decreasing. So decay or exponential decay, it comes from decreasing functions. So especially when you are given half-life, that means that the population is going in half. So as it was said here, if you start with 100 grams, then after 5.2 years, you have 50 grams because 50% has decayed. So after 1 year, for when we have 80 grams, we're trying to solve how much cobalt-60 we have. So N, which is going to be our time period, has to be interpreted in the context of the 5.2 years. So the time period that rate of change applies to is every 5.2 years. So we have to consider how many of those 5.2 year periods have passed. And of course, when we're looking at after 1 year, this 5.2 year periods have not passed completely. So generally, just to write the general equation, we have C of n, which is the amount of cobalt 60 after n 5.2 time period, 5.2 years, is going to be 0.8, which was our, sorry, this should be 80 because it was 80 grams. And so this is the 0.5 is 1 minus 0.5 and to the power of n. So the 1.1 minus 0.5 is just 0.5. And also because we are considering half-life, if you just write 0.5, that's sufficient. I will understand that you understood half-life, so that will be fine. Now we want to determine what that n is because it's, again, remember it's 1 year, so it's not a full, n is not equal to 1. N is equal to 5.2 years, or sorry, when n is equal to 1, this is 5.2 years. So for example, when n would be equal to 2, that's 10.4 years. So when we are looking at 1 year, we have to determine what n is. And so this is just, you can solve using what you know with algebra. So n is actually just 1 divided by 5.2. And so it is 1 year of the 5.2 years. So n is approximately 0.19. And substituting that value in, we have 80 times 0.5 and to the power of 0.19, which gives us 70.13. So after 1 year, approximately 70.13 grams of cobalt-60 will remain. And so going back here, we took this complex problem with like many numbers given to us, and we were able to interpret each of the values to get the final answer that we were looking for, and wasn't as complex as you would have thought at the beginning. And I think this is our last example. An isotope decays to 25% of its original mass after approximately 58 years. Determine its half-life. So, what these questions are asking you when you're asked to determine the half-life is pretty much when is the population half of the original population? So, let H represent the half-life in years. And N0 is going to be the original mass of the isotope. And we don't actually need to know what the original mass was. We can think of it as percentage. So let's say we start with 100%. Then after how much time do we have 50% of that original population? And N of H is then going to represent the mass of the isotope after H years. H years. And so because we are considering half-life, then we want sorry, actually correction here. This one is T. It's this one that I need to change because H being the half-life is what we're trying to find, but if we know the half-life, then that's our known value. So similar to above here, when we had the half-life as 5.2 years, this is the time period that we're looking at. But of course, the variable that's actually changing which is the time, will be dependent on that half-life. So we are looking at N of T after T years, but with respect to that half-life. So that's why when we have the rate as zero point 0.5 or 50%, which is the half-life, then we are looking at how many half-lives have passed with respect to that T years. So, and again, this is N of T. Because T is the one that is changing. Although, yes, we are looking for H, H is going to be constant like, especially after we find what H is, it's going to be constant in terms of our problem, but the number of years T is what's actually changing. So pretty much, 0.5, so half of the initial population. And T over H is going to be exactly as we saw here with 1 over 52. So how many years have passed with respect to the half-life time period? And so what we were given is that after 58 years, then our population was 25%. So starting with a population of 100, then we have 25, and this is with respect to the half-life that happens after H years. So pretty much how many half-lives have occurred in this 58 years. So first dividing by 100, then we get that 1 over 2, which is 0 0.5, to the power of 58 over H is equal to 1/4. So how many half-lives have passed for us to get to a quarter? And of course, this is simple to see that 1 over 4 is just 1 half squared. So I just want these two exponents to be equal. So pretty much 2 is equal to 58 over H, or H is equal to 29. And of course, that makes sense for our half-life to be 29 years, because consider you have a mass of 100%. Then after 29 years, the half-life has happened, so the mass is now 50% of its original amount. And then after another 29 years, this 50% is also halved again. So now we are 25% of the original population. So two half-lives have passed for us to get from 100% of the mass to 25% of the mass. And so your final answer is the half-life is 29 years. And just so you understand that T portion a little better, you may be asked after, for example, 40 years, what is the population? But of course, our rate of change is given with respect to half years or um, half-life and not just years. So then you would be thinking 100% of the population times 0 0.5. And I can't do 40 here because 40 half-lives have not passed. But I'm going to consider out of the 29 years that are my half life, how much time has passed, which is 40 over 29. And if we solve this, you will get 38.44. And this will be approximately 38% of the population. And that makes sense, right? Because we just saw that after 58 years, we have 25% of the population, and after 29 years, we have 50% of the population. So 40 years falls in that between that range, and so does 38% fall between 25% and 50%. And that is the last example of our lesson, and that was our last lesson for exponential functions. So you have some practice problems here to practice application of exponential functions, and I will see you all in our next unit for financial literacy, where you're really going to see the application of exponential functions. As always, don't forget to check Google Classroom for any additional tasks posted, and don't hesitate to reach out if you have any questions, and I will see you all in our next class.